Okay, 2.63 is sort of a revisit of thermodynamics. And if you have taken thermodynamics or you've studied it before, then this should be a very easy sort of refresher problem on everything you've learned in there. But if you haven't, it might feel like there's a lot of things being thrown at you at once. So in the case that, you've never taken thermo before, which shouldn't happen, because realistically, the order in which you should be learning physics should have quantum mechanics at the very end after everything else. But in the off chance that you didn't follow that order, by all means, you can skip this problem without that much issue. It really isn't that difficult. Really, it's just showing you that sort of even though quantum mechanics and thermodynamics sort of use very different mathematical approaches, you can actually link them together and show that you can get results that you got in thermodynamics using just equations from quantum mechanics without any trouble. In another way of saying, like, sort of the methods that you use in quantum mechanics can be interchanged with problems in thermodynamics and sort of give you the same results that you would expect. So we are given this probability function of being in any statistical distribution in a thermodynamical system, and we're also given the partition function z as this equation, and we're given beta as a constant 1 over kt. In part 1, we're not actually trying to link anything. We just want to show that the average thermal energy of a system can be written in this form. So let's start by defining Pn in terms of this Pn that's given to us. So the average energy can be rewritten as the summation of n of En multiplied by Pn, which we're going to replace with 1 over z multiplied by e to the negative beta times e sub n. So all I've done is I'm taking this Pn and I've replaced it with this Pn. At this point, the next thing I can immediately do is I can move 1 over z outside of our summation, because if you look at what z is equal to the summation of e to the negative beta times e sub n. So beta is just a constant, 1 over kt, given some temperature T, and then the summation of all of the valid energies in a system is also going to be a constant. So because of that, z is therefore a constant. It has no dependence on n, therefore it just moves out of the system. So now we have 1 over z times the summation in terms of n of e sub n times e to the negative beta en. Now the next thing I can look at is I can recognize that, I'm supposed to link this into a partial derivative in terms of beta. And if I look at this equation, this looks basically just like the partial derivative of this term in terms of beta. Or, yeah, in terms of beta, because then e sub n gets brought down as a constant. So I can rewrite this, actually, as 1 over z times the summation indexed by n of the negative of the partial derivative with respect to beta of the term e to the negative beta en. Now I'm going to bring the negative out, and I can also recognize that when you're dealing with, partial derivatives and just derivatives in general with respect to summations, assuming that this thing is a partial of the entire term in the summation, I can interchange it with the summation, which means I can just bring out the partial derivative without any issues. So because of that, I have negative 1 over z times the partial with respect to beta of the summation with respect to n of e to the negative beta times en. And now, at this point, we can recognize that this is just quite literally the definition of z, because if we look up here, z is actually just the summation in terms of n of e to the negative beta en. So this is actually equal to negative 1 over z times the partial of z with respect to beta. And this is quite literally just the definition of the derivative of a natural log, because remember, given ln of something, ln of box, the derivative of this is box prime divided by box. So given ln of z, the partial derivative of ln of z with respect to beta is going to be, the partial of z with respect to beta divided by z. So this is actually just equal to negative of the partial with respect to beta of the natural log of z. And with that, we are done with part A. Okay, part B is where we're actually going to start inputting some stuff from quantum mechanics, and what we're going to do is we're going to incorporate the idea that a quantum harmonic oscillator has discrete values of energy defined by m plus 1/2 h bar omega. So if we do this, then we want to show that the partition function z ends up becoming this. And to get it, we have a hint that we're going to need to sum out a geometric series. So if we do this, well, we have our definition of z. It's the summation in terms of n of e to the negative beta times en. So if we input the quantum mechanical definition of En for a quantum harmonic oscillator, then we're going to get that this is a summation from, and now let's define it more concretely, from n equals 0 to n equals infinity of e to the negative beta times n plus 1/2 h bar omega. And from this point we can rewrite this, because note here that if you use distributive property, you're going to get terms that have n and terms that don't have n, and we can move the terms that don't have n outside of our summation. So this is going to become a summation from n equals 0 to infinity of e to the negative beta h bar omega n, and then multiplied by e to the negative beta h bar omega divided by 2. And here we can just move this term out because it has no independence. So we have e to the negative beta h bar omega divided by 2 times the summation from n equals 0 to infinity of e to the negative beta h bar omega n. And now at this point, this term right here is pretty much just a geometric series. So, excuse me, give me 1 second, please. I believe my tablet might be bugging out. Okay, there we go. Hopefully that works a little bit better. Yeah. Okay, so at this point, what we're going to do is we're going to recognize that for a actual geometrical series, the definition for that is that given a summation like this from j equals 0 to, in fact, you know what? Yeah, from j equals 0 to n, so this is the general definition for a geometric series of any initial coefficient a times times a multiplying factor r to the power of j, like this. The solution to this is assuming that, well, okay, let's write the full solution actually, is going to equal ar to the power of n plus 1 minus a divided by r minus 1, given that r doesn't equal 1, and then just n plus 1 times a, given that r is equal to 1. So in this case, our coefficient a is going to equal 1 because we have no coefficients at the front. Our multiplying factor is going to be r is equal to e to the negative beta h bar omega, and then our j term is equal to just n. So immediately I see that r obviously isn't equal to 1, so we're going to look at this top definition. So in that case, our summation is going to be equal, so z is going to equal e to the negative beta times h bar omega over 2 multiplied by our new definition here. So a is equal to 1, so we have e to the negative beta h bar omega to the power of n plus 1 and also in this case, I've made a bit of a mathematical notation error here because j is equal to n and n goes up to infinity. So in this case, this is actually e to the power of infinity, because remember our sum goes from 0 to infinity. So given a summation from 0 to n, this n term is getting replaced with infinity. So this is actually equal to just multiplied by infinity. And then we're subtracting by a, which is going to be 1, and then this is divided by r minus 1, so e to negative beta h bar omega subtracted by 1. And e to the power of negative infinity is just 0, so we have e to the negative beta h bar omega divided by 2, and this is going to get multiplied by, I'm going to change the order, so we have 0 minus 1 or negative 1. I'm going to change it to positive 1 and switch the order down below to 1 minus e to the negative beta h bar omega, like that. And then if I move this up to the top, this is just equal to e to the negative beta h bar omega over half divided by 1 minus e to the negative beta h bar omega. And just like that, we are done with this problem. Or not this problem, but with this part. Okay, now that we're at this point, part C, we're going to throw everything together and redefine a new average thermal energy in terms of our quantum mechanical energy values. So we have the results from part A and part B, which is that from part A, we concluded that the average energy can be rewritten in this form. In part B, we found that our new partition function defined in terms of the quantum mechanical discrete energies is this. We want to now show that we can rewrite the average energy as this form. So let's do that. E average is going to equal, first off, negative of the reciprocal of z, so negative 1 minus e to the negative beta h bar omega, divided by e to the negative beta h bar omega over half, and then the derivative of this term. So in general, the definition is that whenever we have a function that's equal to box divided by triangle, the derivative of that function is box prime times triangle minus triangle prime times box divided by triangle squared. So in our case, our box term is e to the negative beta h bar omega over 2. So our box prime term is going to be negative h bar omega over 2 times e to the negative beta h bar omega over 2. Triangle is 1 minus e to the negative beta h bar omega, and triangle prime is, let's see, h bar omega e to the negative beta h bar omega, I believe. Because that goes to 0, the negative cancels out to make a positive, yeah. Okay, so if we write it like this, then we have box prime, so negative h bar omega over 2 times e to the negative beta h bar omega over 2 times triangle, which is 1 minus, actually, you know what? Let's move this down a little bit to make it a little bit less crowded. Okay, so box prime times triangle, which is 1 minus e to the negative beta h bar omega, minus triangle prime times box, I believe. Yeah, minus triangle prime times box. So minus h bar omega times box, so e to the negative 1 minus 1/2, so negative 3 beta h bar omega over 2. And this is all divided by triangle squared, which is going to be 1 minus e to the negative beta h bar omega squared. So immediately, I can cancel out one of these terms with this term. So what I'm left with is, and you know what, let's also get the negative out of the way. So we have, let's see, 1 over e to the negative beta h bar omega over 2 multiplied by h bar omega over 2 e to the negative beta h bar omega over 2 times 1 minus e to the negative beta h bar omega plus h bar omega times e to the negative 3 beta h bar omega over 2, and this is all divided by 1 minus e to the negative beta h bar omega, like that. Okay, now let's do a little bit of distributive. So this is going to be 1 over e to the negative beta h bar omega over 2 multiplied by h bar omega over 2 e to the negative beta h bar omega over 2. So that's multiplied by 1, that's fine, and then subtracted by h bar omega over 2 e to the power of negative 3 beta h bar omega over 2. Because the positive and the negative makes a negative, we have h bar omega over 2, and then negative 1/2 minus 1 is negative 3/2. And then finally, plus h bar omega e to the negative 3 beta h bar omega over 2. And then this is all divided by 1 minus e to the negative beta h bar omega. Did I make a mistake here? No, I did not. Okay. So immediately, the next thing I see is I can cancel out e to the negative beta h bar omega over with everything. So this is going to give me h bar omega over 2. So this cancels with the e to the negative beta h bar omega over 2 cancels with each of these terms. So minus h bar omega over 2 times e to the just negative beta h bar omega plus h bar omega e to the negative beta h bar omega, like that. And then this is all divided by 1 minus e to the negative beta h bar omega. At this point, we can combine these terms. We get h bar omega over 2 subtracted. So this is, let's see, negative h bar omega over 2 plus h bar omega. So this is just going to be h bar omega over 2, I believe. Yeah, plus h bar omega over 2 times e to the negative beta h bar omega divided by 1 minus e to the negative beta h bar omega. And at this point, I factor out the h bar omega over 2, and I'm multiplying 1 plus e to the negative beta h bar omega over 1 minus e to the negative beta h bar omega. And if I look above it, what I'm supposed to get, this is indeed the expected answer. So with that, we are done with part C. So part D is now going to introduce the heat capacity. So as a quick refresher, the heat capacity is defined as the amount of energy that's required to raise the temperature of a given system by 1 degree Kelvin. So if C equals 26, for example, this would translate to requiring 26 joules of energy to raise the temperature of a system by 1 degree Kelvin. So in this case, since we have the average energy defined by this, we could say that for a single harmonic oscillator, so C of quantum harmonic oscillator, this is just equal to the partial derivative of the average energy we found up here with respect to temperature, because this gives us the rate at which energy changes with respect to temperature, which is therefore the amount of energy that is required to raise temperature by 1 degree. Now, what this is telling us is that a crystal of n atoms can be thought of as sort of a collection of 3n oscillators. So what we mean by that is if you look at an atom, right? If you think of an atom as a 3D lattice, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? If you think of an atom as this sort of 3D lattice, let me just draw it out all the way. Then any given atom in this lattice, let's see if I can get this. Let's see if I can get this drawing a little bit more accurate by drawing the back legs in red. If you think of a given atom in this lattice, let's say this red dot is the middle atom in this lattice, then it has multiple different connections, right? Because it has a connection to the top middle atom. So I'm going to draw these as springs because that's what they are, right? It has a connection to the bottom middle atom, which is like right around here. It has a connection to the 2 side atoms, right around here and right around here. And it has a connection to the front atoms and the back atoms. So basically, if you think of this as like a cube, then an atom in the middle, if you think of the cube as a lattice, is going to have connections on the up-down faces, the top, front, back faces, and the left-right faces. So because of that, we can think of this as just 3 harmonic oscillators. One of them is in X, one of them is Y, and the third one is in Z. So because of that, we can say that the heat capacity of a crystal is therefore going to be 3 times the heat capacity of a single quantum harmonic oscillator, since each individual atom is composed of 3 separate harmonic oscillators. So we want to prove that by using this formula, we get this result. So let's write that out now. So C is equal to 3 times the partial of the expectation value of the energy divided by, or with respect to temperature. And we want to show that it's equal to 3 kb times theta e over t squared times e to the theta e t over e to the theta e over t minus 1 squared. So theta e is defined as h bar omega over k. So let's write this out fully. This is apparently equal to 3 times k times h bar omega over kt. Whoops, let's make this a little bit neater. Kt squared times e to the h bar omega over kt divided by e to the h bar omega over kt minus 1 squared. So somehow we want to show this, or more realistically, or more simply, we can just get rid of the 3 altogether. We're trying to show that the partial of e with respect to t is equal to k times h bar omega over kt squared times e to the h bar omega over kt divided by e to the h bar omega over kt minus 1 squared. And we have our definition of E from up above, which is this. Let's write this out. That E is equal to this. So once again, we're going to have to use quotient rule. So let's write out our boxes and triangles. So actually, you know what? Before even that, we have to write out this in terms of beta, actually. So we have the definition from way back up here that beta is equal to 1 over kt. So if we write this out in that way, we get E is equal to h bar omega over 2 times 1 plus e to the negative h bar omega over kt, so divided by 1 minus e to the negative h bar omega over kt, like that. So in that case, we now have that box is equal to 1 plus e to the negative h bar omega over kt. Box prime is equal to, let's see, we're deriving with respect to temperature. Oh, so that's a little bit more tricky. This is actually equal to 1 plus e to the negative h bar omega over k times t to the negative 1 power. So in that case, the derivative is, let's see, h bar omega over k e times t to the negative 2nd power e to the negative h bar omega over k t to the negative 1st power, I believe. Is that correct? Yeah. Yep. Okay. And then triangle is 1 minus e to the negative h bar omega over k t to the negative 1st power. So the derivative is going to be the same. H bar, actually no, there's going to be a negative at the front, because let's see, we're bringing down a negative h bar omega over k t to the negative 2nd power e to the negative h bar omega over k t to the negative 1st power. Okay, now let's write this out fully. So the partial of E with respect to temperature is going to be h bar omega over 2 multiplied by box prime times triangle. So this is going to, let's see, h bar omega over kt squared times e to the negative h bar omega over kt multiplied by 1 minus e to the negative h bar omega over kt. Excuse me. Box prime times triangle minus triangle prime times box. So I'm going to cancel out the minuses. This is going to be plus h bar omega over kt squared times e to the negative h bar omega over kt multiplied by 1 plus e to the negative h bar omega over kt, like that. And then we're dividing this by triangle squared. So 1 minus e to the negative h bar omega over kt squared, like that. Okay, now let's do a little bit of cancellation and distribution. So first off, immediately I see that I can factor out this common term. So h bar omega over 2 times h bar omega over kt squared times e to the negative h bar omega over kt. And this is then done by 1 minus e to the negative h bar omega over kt plus 1 plus e to the negative h bar omega over kt divided by 1 minus e to the negative h bar omega over kt squared. At this point, these two terms cancel. The top is going to give me 2. So this is equal to h bar omega over 2 times h bar omega over kt squared e to the negative h bar omega over kt times, and you know what? Actually, the 2 just straight up cancels out with the 2 down here, so this is just going to give me h bar omega over here multiplied by 1 over 1 minus e to the negative h bar omega over kt squared. Now let's look back up and see what we're supposed to be getting, so we can massage our equation to look something more like this, right? So this is what we're trying to get. So I'm going to circle this in red. Okay, so what do I see here? The first thing I see is that I want to get this. So let's see. I'm going to get h bar squared omega squared over kt squared multiplied by e to the negative h bar omega over kt divided by 1 minus e to the negative h bar omega over kt squared. So the first thing I can do is this term does indeed simplify to that, so this is just k times h bar omega over kt squared, because the k squared at the bottom gets cancelled out with the k at the top. This gives me just a k at the bottom. And now our main problem is doing this thing. So e to the negative h bar omega over kt times 1 minus e to the negative h bar omega over kt squared. So what this suggests is that if I multiply both sides by e to the power of 2h bar omega over kt, the bottom should turn into the opposite. So let's see if we can do that. So I'm going to multiply by e to the 2h bar omega t, or sorry, 2h bar over kt, e to the 2h bar omega over kt over e to the 2h bar omega over kt. Is that correct? Yeah, so the top becomes e to the h bar over kt. Now the bottom is the thing that we're concerned about. So let's see. 1 minus e to the negative h bar omega over kt times 1 minus e to the negative h bar omega over kt. This is going to equal 1 minus, let's see, 1 minus e minus e. So minus 2e to the negative h bar omega over kt, I believe. Yeah. And then plus e to the negative 2 h bar omega over kt. Like that. Is that correct? Plus e to the negative, yeah. And then if I multiply this thing, so in orange, if I then multiply this thing by my bottom factor of e to the 2h bar omega over kt, then this is going to give me, I'm going to switch them around. So these two terms make 1, and we can get minus 2 e to the positive h bar omega over kt plus e to the 2h bar omega over kt, right? Yeah. So if I then compare that to what I'm expected to get, which is e to the h bar omega over kt minus 1 squared, so e to the h bar omega over kt minus 1 times e to the h bar omega over kt minus 1, this is going to give me e to the 2h bar omega over kt minus 2 e to the h bar omega over kt plus 1, which is indeed exactly equal to up here. So therefore, this bottom term does in fact simplify to this upper term, and therefore we are done with this part of the problem. In part E, we are asked to sketch the graph of c over k versus t over theta e, and we are told that our result should look like this. So if you ever took a thermodynamics class, you would know that this is sort of the expected outcome for sort of the specific heat versus temperature when analyzing a substance using Boltzmann statistics. So what we're saying is that instead of using Boltzmann statistics, we analyze this with a mix of Boltzmann statistics and also quantum mechanics. We should get the same result, assuming that quantum mechanics is a valid form of physics, which it is. So because of that, we are told to graph. So let's start by analyzing c over kb. So we have c here, therefore c over kb is going to equal 3 times theta e over t squared times e to the power of theta e over t divided by e to the theta e over t minus 1 squared. And at this point, our graph, our x-axis, is going to be t over theta e. So if we say that, you know, our y term is equal to c over kb, and we want y of x where x is equal to t over theta e, then our goal is to take this equation and convert it into the variable x form. So we see that this is just going to be 3 times 1 over x squared, right? Because 1 over x is going to be theta e over t times e to the power of 1 over x divided by e to the power of 1 over x minus 1 squared. And if this is our y function, then now our task is just to shove this into Desmos and basically graph this out. and I've already done this, the resulting function looks something like this. So what we see here is basically just a more exaggerated version of this, where our middle slope is a lot steeper, but it still follows the general curvature, which is that, you know, it starts out with a very small slope, becomes bigger, and then becomes smaller again. The actual reason behind why this is a thing is more regulated to something that you would learn in thermodynamics on a very basic level, or sort of as a very brief sort of review of this. Any given system of particles has multiple degrees of freedom. So at lower temperatures, the degrees of freedom you have are less, and at higher temperatures, the degrees of freedom you have are more. So at lower temperatures, you might only have like vibration in the X, Y, and Z axis. But if you increase sort of the temperature, you start unlocking higher degrees of freedom via the form of things like rotation and stuff like that. So I believe the standard order that you learn when you first get introduced to this is that at very low temperatures, you only have kinematic freedom. So you have freedom with translation in the X, Y, and Z directions. So basically your particle moves, it translates in X, Y, and Z. Increase the temperature a little bit and you can start introducing vibrational modes of freedom, which involve, you know, the particle can now vibrate in X, Y, and Z in addition to moving in X, Y, and Z. And then increase the temperature even more, you start introducing rotational degrees of freedom and things like that. And pretty much all of these things will change your resulting specific heat C value. So as you unlock more of these degrees of freedom, the specific heat is going to change in accordance with that. But that is something that is, if you want to learn in more detail, you have to go to thermodynamics. Right now, this is quantum mechanics, so really we're just trying to match our results with the expected thermodynamics result, and we see that it does. So sort of we've achieved the key point that this problem is trying to prove, which is that, you know, even though quantum mechanics seems like this big thing that's very different from all the other branches of physics we've learned so far, it can still sort of be used to get results that we got back in thermodynamics or electrodynamics or classical mechanics. In fact, we've had problems earlier in this book that linked classical mechanical problems to quantum mechanical solutions. I believe one of them involved modeling like a ball falling off of a cliff and analyzing the probability of where the ball is. And I think the result is something that looks very similar to like the kinematic equation equivalent. So basically, you know, the key point is, even though sort of in all these different areas of physics you use different types of math, they technically are all correct and can be interchanged with each other. So you can technically find expected answers from classical mechanics using techniques from quantum mechanics, and vice versa with any other type of field of physics. That being said, it's always easier to use the field of math that is intended for a given physics system. So, you know, thermodynamics is always best described using statistical mathematics, and then quantum mechanics is always technically best represented using linear algebra, and classical mechanics is always best represented just using basic math. So it's sort of like you could do it, and the reason why we do it is to sort of show that these ideas we're developing are in fact related to each other, and they're all valid ways of interpreting the world around us. It's just that using them outside of their intended purpose creates a lot more complexity than you would need. You know, if you try to analyze sort of something like a room filled with air molecules by analyzing each individual molecule with kinematic techniques like using force equals mass times acceleration, you would basically be stuck doing this for the rest of your life, and you probably wouldn't finish the problem, because think about the number of air molecules that are actually in something even as small as like a 1 centimeter cubed box, right? It would be like hundreds of thousands of millions of trillions. So you would have to set up a system for each of those, whereas in contrast to that, if you just used statistical mechanics to analyze it, then you would be done in like a few minutes. So yeah, that's really the key point here for this problem.